else. Tomorrow we will be in the lab. We're going to be in the lab today, but today is not a, we don't need to take any safety precautions. Tomorrow we will. Tomorrow our lab will involve fire. So please bring hair ties if you have long hair. Long hair must be tied up. And I have safety goggles and glasses in there, so you don't need to worry about that, but I don't have hair ties for obvious reasons. So yeah, that's on you to bring. It's got to be tied up because I don't want your hair falling in the fire. That's not going to be fun. So please bring hair ties tomorrow, and we're going to be burning some stuff in the lab, looking at some cool properties of light. It'll be very interesting and fun. I think it's a cool way to kind of wind down before Christmas break. So please bring hair ties, and we'll be good there. Questions about that? Okay, awesome. Maybe I should ask somebody if I can have some. Okay, let's pick up yesterday where we left off. We took a tour of the electromagnetic spectrum. Tell me about, trying to think of a good question. Tell me about wavelength, frequency, and energy. Nathan? Okay, so he says wavelength and frequency are inversely related. Do we agree with that? You know what that means? It means one goes up, the other goes down. So yes, right? The longer the wave is, the less waves that can pass by. So the longer the wavelength, the lower the frequency. I definitely agree with that. And then he says frequency and energy are directly related. Meaning if one goes up, the other will also go up. Do we agree with that? Yep, I agree with that too, right? The more waves that pass by per second, then you can deliver more energy. So yep, higher frequency, higher energy, that makes sense to me as well. Let's see. If we're thinking about the spectrum, Abby, tell me about, well, which end of the spectrum's got really long waves with low frequencies and low energy? Well, it might not be left, right? That's just kind of how we put it. What do they call them? The radio ones, okay? So the radio end of the spectrum, okay? Because you could flip the spectrum around, right? It's kind of arbitrary which way it looks. But yes, radio end, right, is very long wavelengths, which means low frequency and very low energy. Okay. Let's see. Guessing what's right in the middle.
This.
Right in the middle of the spectrum.
What's it called? It's like colors, you know?
Visible.
Yeah.
Yep, the colors. Okay, the visible light. The light. Why do we call it visible?
Because you can see that.
Because we can see it, right? That's the whole point, right? We have that tiny little sliver in the spectrum, really just because it's of particular interest to us, because that's what our eyes are sensitive to. We can see that. Okay, and then on the other side of the spectrum, Brody, tell me about the high frequency side. It's over there.
They get high enough.
Definitely high enough that it can hurt you, right? What kinds of stuff's on that side?
Like gamma rays and
Perfect. Yep. So we got gamma on the far end of that side, and then just before gamma would be X-rays. With both of those very high frequency, high energy waves, definitely high enough to damage our cells if we are exposed to it long enough. All right. I guess I wanted to show you this. This is kind of the last thing I had as part of this little thing. It's a cool little tool that lets you kind of see scales of things. Got weird background music. I'm gonna turn that down. But I think it's a good little tool. So if I zoom out just a tiny bit, right here, you've got FM radio wavelength. Okay, so just to kind of give you an idea of how long these things typically are, it's typically about the length, you know, a meter or two. Okay? But again, radio waves can be as long as football fields. But that's your typical FM radio wavelength. And so as we start to go down, here we have, you know, regularly sized objects, birds, mice, eggs, pennies, things of that nature. And then we keep getting smaller. Right, we're getting down to the level of insects, and then even smaller, we're at thicknesses of paper and human hair. Okay, and right there is your infrared wavelength. Okay. If you do I don't know, it looks maybe like a fourth of the thickness of human hair. And so an infrared is pretty small. And then we can keep going. We're starting to get on the order of cells. And right there, you have red light wavelength. The wavelength of red light looks to be about the thickness of a chromosome. If I keep going, a little bit smaller, right there, there's violet light. We're still on a wavelength the size of about scales. If I keep going, there's ultraviolet right there. It's even smaller than a typical cell. These are about the size of like a virus. Keep zooming in. Now we're getting into like parts of a cell. So we have DNA, phospholipids. Now we've got right here an X-ray wavelength, okay, about the length of typical glucose molecule of sugar. And now right there is the cesium atom. Look at your periodic tables on the back cover. Okay, back cover your study guide, look at the periodic table. Which element would you expect to have a large atomic radius? Where are you going to look? Bottom left, right? So we expect francium to be our biggest one. We don't know a whole lot about francium because it's very rare. So we know about cesium though. We've had a lot of large samples of cesium, and we know cesium is a large atom. Hence why it's the first one we see here as we're zooming in from large scale to small scale. So keep going. Right there, we've got even smaller atoms like carbon. There's a water molecule there. Hydrogen atom and helium atom. And we keep going all the way down here, and there's our gamma ray. Okay. The wavelength of that gamma ray is, you can see it, that much smaller than a helium atom, which a helium atom is going to be the smallest atomic radius on the periodic table. Okay. And I also like this little part of it. If you keep zooming in even more and more and more, you actually start to see size of nuclei. So here's your helium nucleus. See if you can keep your eye on it as I zoom out to the actual atom. Just to kind of give you an idea how small the nucleus is, right? But I kind of like this tool, helps us see how small these wavelengths actually get. But I'll put this on canvas because you can go the opposite direction too. You can start to see how big things get. It's a cool little thing. All right. So, any questions regarding electromagnetic spectrum? And let's do a couple of questions. Talk through tables. Which type of electromagnetic radiation listed has the longest wavelength? Talk through tables. Okay, I think I heard everybody say radio for that one. Which type of electromagnetic radiation listed has the highest frequency? Okay, I'd be looking for X-rays as well. Okay, what about which one has the highest energy?
Yeah.
Why does gamma have the highest energy? Because it has the highest frequency. Perfect. All right, I think we're pretty good there. All right, so I would need you to go to page 8. Everybody go to page 8. On page 8, I want you to do questions 1 through 6. Okay, questions 1 through 6. I think I put my colors into the lab, so I'll go grab those. If you want to use colors on this page. Over here is colors. You want to get colors, color in that page. We'll go ahead and do 1 through 6. You can work through tables. I don't think it'll take you very long. We've already talked about all this stuff. I just want to make sure you get this fill in. Page 8, 1 through 6. Indigo is kind of a funny story. So when Isaac Newton first passed white light through a prism, and he saw kind of a spectrum of colors, because it's not really definable in colors spectrum. He first identified 5 colors, but then he thought maybe there's a connection between light and musical scale, and so he tried to add 2 more. And so he found quote unquote 7 colors, but those are completely different. There really is no red either. It's just kind of a smooth transition from color to color. That's what it makes up sometimes. Because you want 7. So a couple more minutes here, it shouldn't take too long to get it filled in. I'm kind of rushing it because I want to get in the lab and do something cool today. Okay, we'll go one more minute, try and get the questions filled in. You can kind of shade colors in as we go a little bit later. We'll make sure those questions are done. Okay, so let's talk for a minute. Number 2, what happens to white light when it passes through a prism? Everybody. It splits up into its individual colors, which we know are correspondent to different wavelengths of light. Okay, I was talking to Amaya about this, but Isaac Newton did this way back in 1700, whatever, and he noticed obviously the splitting of colors, which he found very cool, but he divided it at first into 5 colors, which again is completely arbitrary, right? It's a spectrum of color. To our eyes, there really isn't any division. It's just a spectrum. It goes, continuously from one end to the other. So Isaac Newton kind of just picked out colors because he was familiar with them. And then he thought, well, there might be a connection to the musical scale. And so he tried to add 2 more colors. So he added like indigo, and I think he added violet. So again, those are just random divisions. They don't really have, and there is no connection between the light and the musical scale. So these colors really are random divisions that we made up just to kind of help ourselves out. Because you could argue there's another color that's in between red and orange. And, Crayola probably gave that a name like tangerine or something weird like that. But you could argue there's a color between green and yellow that is called, I don't know, dying grass or something. I have no idea, right? These are random divisions, but it is a spectrum. We can't tell the difference. We can't see any real divisions here. Number 3, why are the color labels in the table in model 1 plural? I think I kind of gave you the answer to that, right? Exactly. There is no one red. There's a spectrum of red, that slowly changes into orange, that slowly changes into yellow, right? It's all kind of just a slow transition. There is no one red or one yellow. Number 4, do all colors of light travel at the same speed?
No.
Yes. Yes, they do. Okay. I know it's weird to think about, right? Because we have all these different colors of light. We know they have different energies, different frequencies, different wavelengths. So it kind of makes sense that we would think they'd have different speeds. They don't. All travel at the same speed. You remember what the speed is? It's 3 × 10⁸, right? A 3 with 8 zeros after it, meters per second. Really, really fast. Number 5, do all colors of light have the same energy? Of course not, right? We know they have different energies. So which one has the highest energy? Violets and purples are going to have high energies, which means reds are going to have low energies. Okay, number 6, consider the light illustrated in model 1. Which color corresponds to the longest wavelength? Red. Which color corresponds to the shortest wavelength? Violets. And it says write a sentence that describes the relationship between wavelength and energy. I like it. Short wavelength, high energy. Long wavelength, low energy. Perfect. Okay, very good, very good. So I do not want to lose sight of the big picture though. Okay, Cass, why do we care about light?
Because we see it like everywhere.
I mean, that's
We
true.
kinda need it to live.
You're right, you're right. I will give you that, but
Yeah.
go take physics. Physics will kind of give you even more cool stuff about why we care about light. Why do we as chemists care about light? What does light tell us about matter and stuff like that? We talked about it last unit, right at the end, right? What happens when an electron absorbs energy? No,
No, it goes into more excited.
it rises in energy level, right? It goes to an excited state. What happens when an electron releases energy? Then it drops down in energy level, but that energy is usually given off in the form of light. So if we can get a good analysis of these colors, of these different lights given off by atoms, then we can identify what stuff is actually made of. That's why we care. That's why light is of particular interest to us. Okay, turn the page. So page 9 and 10. I just want you to look at this diagram up at the top. We are going to go into the lab and we are going to use what's called spectral tubes or gas discharge tubes. Eyes up. These tubes are filled with elemental gases, right? Different elements that are in the gas phase. What we're going to do is pass a really high voltage current through them, okay? Pass a lot of electrical energy, and that's going to excite the electrons inside. Okay, so they're going to go up in energy. And then when they lose some of that energy and they go back down, they will give off that energy as light. That's why these tubes are going to light up. And they're going to be really cool colors. And then you're going to use not a prism, the diagram has a prism, you're going to use a different thing called the spectroscope, and I'll show you how that works in a minute. But the spectroscope will split that light into its component colors. And we'll be able to analyze really what the element is based on the colors that come out of the spectroscope. Okay, it's a very cool process how it works. So turn to page 11. Okay, quickly turn to page 11. Take like a minute and a half, fill in 19 and 20 with your tables. Go.
Oh, wait, is it absorber? Because it looks like they're pointing down. The lower down
Yeah. They're going from
It's just going and it also has a highest frequency. Yeah.
Oh.
Okay, 30 more seconds. Okay, number 19. Which diagram shows an electron moving from level 5 to level 2? That would be B, right? Because the innermost is 1, the outermost is 6. So B shows 5 to 2. 19A, in the model above, is energy being released or absorbed? Okay, we're talking about releasing energy, right? We're going down in energy level, so we're giving these electrons are giving away some energy. Part B, the electrons in the models are moving from a lower or higher energy level to a lower or higher energy state. We're going high to low, right? High to low, and all of them, high to low. C, is light absorbed or released? Okay, it's released, right? And in this case, the energy and light is kind of synonymous. The energy being released is in the form of light. Okay, number 20, consider the energy transitions represented in the models. Which one shows the highest transition? That would be A, right? 6 to 2, that's the biggest jump. Okay, B says give 2 pieces of evidence for your answer in 20A. How do you know that A has the biggest energy jump?
It has the most force,
What do you mean the most force?
like it has the most rings that it goes through.
Okay, so we have the largest, arrow here, right? The biggest jump. What else? Yeah, if you look at this little light wave given off here, it has the lowest wavelength, which we know means the highest energy. Okay, whereas this one has a small jump and its light given off is very long in wavelength, so we know it's low energy. Okay, C, rank the models based on highest to lowest energy change. Everybody? A, B, C, D, should be pretty easy. D, explain your ranking of the models. Again, this is kind of the same thing as part B. A, I know that I can rank them that way because the arrows represent the biggest change, but also the wavelengths of the light given off can tell me more about how much energy was released. The shorter the wavelength, the more energy that was given off in those problems. Okay, nice job. So I think we're about ready to head to the lab. Okay, turn to page 5, just a couple more little bits of information. Okay. Up to this point, we have talked about light as a wave, okay, with wavelengths and frequencies and amplitudes. But light gets a little bit more complicated. In the late 18th and it would be the late 19th and early 20th centuries, scientists started to find some weird things about light. It did things that other waves don't do, like sound or like ripples on a pond. It had weird behaviors. So I'm going to show this video. I want you to see how much stuff you can fill in. You might not be able to get all of it, but you should be able to get a few of these questions filled in from this video I'm going to show you.
You look down and see a yellow pencil lying on your desk. Your eyes and then your brain are collecting all sorts of information about the pencil, its size, color, shape, distance, and more. But how exactly does this happen? The ancient Greeks were the first to think more or less scientifically about what light is and how vision works. Some Greek philosophers, including Plato and Pythagoras, thought that light originated in our eyes and that vision happened when little invisible probes were sent to gather information about faraway objects. It took over 1,000 years before the Arab scientist Al-Hasan figured out that the old Greek theory of light couldn't be right. In Al-Hasan's picture, your eyes don't send out invisible intelligence-gathering probes. They simply collect the light that falls into them. Al-Hasan's theory accounts for a fact that the Greeks couldn't easily explain: why it gets dark sometimes. The idea is that very few objects actually emit their own light. The special light-emitting objects, like the sun or a light bulb, are known as sources of light. Most of the things we see, like that pencil on your desk, are simply reflecting light from a source, rather than producing their own. So when you look at your pencil, the light that hits your eye actually originated at the sun and has traveled millions of miles across empty space before bouncing off the pencil and into your eye, which is pretty cool when you think about it. But what exactly is the stuff that's emitted from the sun, and how do we see it? Is it a particle, like atoms, or is it a wave, like ripples on the surface of a pond? Scientists in the modern era would spend a couple of hundred years figuring out the answer to this question. Isaac Newton was one of the earliest. Newton believed that light is made up of tiny, atom-like particles, which he called corpuscles. Using this assumption, he was able to explain some properties of light. For example, refraction, which is how a beam of light appears to bend as it passes from air into water. But in science, even geniuses sometimes get things wrong. In the 19th century, long after Newton died, scientists did a series of experiments that clearly showed that light can't be made up of tiny atom-like particles. For one thing, two beams of light that cross paths don't interact with each other at all. If light were made of tiny solid balls, then you would expect that some of the particles from beam A would crash into some of the particles from beam B. If that happened, the two particles involved in the collision would bounce off in random directions. But that doesn't happen. The beams of light pass right through each other, as you can check for yourself with two laser pointers and some chalk dust. For another thing, light makes interference patterns. Interference patterns are the complicated undulations that happen when two wave patterns occupy the same space. They can be seen when two objects disturb the surface of a still pond, and also when two point-like sources of light are placed near each other. Only waves make interference patterns, particles don't. And as a bonus, understanding that light acts like a wave leads naturally to an explanation of what color is, and why that pencil looks yellow. So it's settled then, light is a wave, right? Not so fast. In the 20th century, scientists did experiments that appeared to show light acting like a particle. For instance, when you shine light on a metal, the light transfers its energy to the atoms in the metal in discrete packets called quanta. But we can't just forget about properties like interference either. So these quanta of light aren't at all like the tiny hard spheres Newton imagined. This results that light sometimes behaves like a particle and sometimes behaves like a wave, led to a revolutionary new physics theory called quantum mechanics. So after all that, let's go back to the question, what is light? Well, light isn't really like anything we're used to dealing with in our everyday lives. Sometimes it behaves like a particle, and other times it behaves like a wave, but it isn't exactly like either.
Okay. I'm gonna skip over this video. Okay, let's talk about part A at the top. Okay, the photoelectric effect. And photoelectric effect looks like this. You shine light with sufficient energy on a metal, you can actually start to knock electrons off the surface of that metal. Okay? So in this particular example, the threshold of enough energy would be green wavelength of light. Okay? Red would not have sufficient energy. You could shine as much red wavelength on that surface as you wanted. You would not be able to get any electrons off. But as soon as you start shining even a little bit of green light, that has sufficient energy to knock off these electrons. Now we know that it's not really knocking off. What's happening is these electrons are being excited. They're absorbing these energies, and there's enough energy that they absorb that they actually become stripped away from their atoms. and they can fly off and kind of do their own thing. Okay. First discovered by Albert Einstein, and this is what won him his Nobel Prize, which I think is kind of weird if you think about it, because that guy was like ridiculously smart and thought of so many different things. This was the thing that got him the Nobel Prize, which is pretty cool though, because I mean, this gave us a lot of insight as to what light is, and because we thought for a long time it was a stream of like atoms, then we thought nope, it's a wave, and Albert Einstein says, hey, what about both? Which is weird. Things can't be both, but somehow light is. Okay. Right here we have another scientist of interest named Max Planck. Okay, and he postulates this idea that energy is emitted in small specific amounts. Okay, the video calls it quanta, so a quantum of energy. If you remember the analogy we talked about last unit, it's like stairs or like keys on a piano, right? Each individual stair represents a specific amount of energy. You can't have an energy amount in between. Okay. Oh, so all that filled out before I turn the page. Okay. Yeah, we got Max Planck believed energy is not emitted continuously like waves, but rather in small specific amounts, which you can put in parentheses, that's called quanta or quantum. Okay. Yeah, talk about this. So we have small specific amounts. And so at the beginning of the 20th century, early 1900s, we have this new idea introduced by Max Planck and later expanded by Albert Einstein, that light is not just a little atom-like particle, but it's not just a wave either. It has properties of both waves and a stream of particles. Under particular circumstances, it can do either one of these things. And it just kind of depends on what you do to it and what you're looking for. Yeah.
What's the question for?
Which one?
Albert Einstein expanded.
We'll get to that in a second. Yep. Yep, we'll get there. Don't worry. Okay. And I guess you can probably fill it in. I'm trying to think where I have it. I mean, really, you can put it, you can do right. Albert Einstein expanded Planck's theory by stating that electromagnetic radiation has a particle-like nature. Okay. Because we had all this evidence before Albert Einstein that light was a wave, right? We have interference and we have wavelengths and frequencies, but now we have this new evidence from Einstein that light has a particle-like nature. Okay. So electromagnetic radiation is only absorbed or released in these whole number of photons. And this photon is really this name that we give to this particle of light. It's a zero mass particle, which that's hard to think about, right? And you think about a particle that has energy, but it has no mass. And still, even to this day, hard for me to wrap my mind around that, but a photon is a zero mass particle of light carrying a very specific amount of energy. Okay. The higher the wavelength of, or sorry, the lower the wavelength of light, the more energy that photon will carry. Okay. So if we're looking at a particular atom, like say hydrogen, if an atom is in the ground state, we know that means it has the lowest possible energy of the atom. And if an electron is in an excited state, then that means it has a higher energy than the ground state. We can have multiple excited states, kind of like you saw in those diagrams. We know that when an atom absorbs energy in the form of electromagnetic radiation or light, it moves up in energy level. And then when an excited electron returns back to its ground state, it gives off electromagnetic radiation. It gives off light. Give me a second to kind of fill everything in. Okay. And I'm going to show a quick video just to help you guys kind of try and picture how light can be both a wave and a particle at the same time.
We see particle-like behavior every day. We drop a ball on the ground and it follows a single trajectory. Leave your giraffe parked on the street, and when you come back, it's still there, just one giraffe. And we see wave behavior too. Toot your horn, and waves spread out through the air, carrying sound to the ears of anyone around. Or drive a boat through water, and waves travel outwards along the surface. But when it comes to the physics of the very small, what we see is a wave-particle duality. Sometimes very small things, we're talking electrons and protons here, behave like particles, and sometimes they behave like waves, flip-floppers. For example, if you release an electron, it'll travel outward as a wave through the room, but when it hits the wall, it'll only hit in one place. You started with one electron, after all. So what if sound had a wave-particle duality? When you shouted, the sound waves would spread outwards in all directions, but only one person could hear what you said. Or when you drove your boat through the water, the waves would travel like normal, but only hit the shore in one place. Now that would make for some pretty boring surfing.
Just a few examples of some weird things light does. And it has properties of both. Okay, so here's what your spectroscope is going to look like. Okay, we'll look at some white light first, but the light will pass in through the spectroscope. It's going to bounce off what's called the diffraction grating, which is going to split the light into its component parts. And then you'll have a screen over here with a little wavelength scale, and that will tell you what each wavelength of the light corresponds to. And the colors are going to be super cool. I think you're going to enjoy looking at these colors. I think last thing on page 5, the frequency of radiation given off corresponds to a specific amount of energy. I think that's the last thing to fill in on page 5. Frequency of radiation given off corresponds to a specific amount of energy, a quanta of energy. Okay, so when we look at hydrogen, for example, we're going to see basically 4 lines that look like this. And each line will correspond to a specific energy from those electron transition states. And different atoms are going to have different, what we call emission lines. These lines will tell us exactly what's inside that tube. Because we have a nice little library, we can then look at an unknown element and say, well, its lines match up with this element, so I must know what's inside. Okay, the hydrogen one's of particular, I guess, interest because it's very easy to analyze a hydrogen atom. We know there's these 4 lines that we're going to see, so we can very easily tell exactly which line corresponds to a particular energy. So when you go in there, you're going to see a red line. That means you are seeing an electron jump from level 3 to level 2. You're going to see a green line. That means you're seeing electrons drop down from 4 to 2. You're going to see a blue line. That means you're seeing electrons jumping down from 5 to 2. And finally, the purple line, you're seeing electrons jump down from 6 to 2. Okay. As we go up to different atoms, things get a little bit more complicated. But for hydrogen, we can identify very specifically what's going on. Okay. So I have enough spectroscopes for every pair to have their own. Okay. So just kind of pair up with the person next to you. If you're at a table of 3, the odd person out can have their own. I think I have like 18 of them. So, but I don't have enough for everybody. So if you need to share, please share. We can worry about coloring tomorrow. For right now, just take a pencil. And then what you'll do on that worksheet I gave you is you'll see something that looks like this inside the spectroscope. And with white light, it'll look like a spectrum, but with lines, like with these, you'll have an individual line to color on. We'll color tomorrow, so just use your pencil and kind of mark on the scale where that line would be. We will color them in tomorrow. Sound good? All right, here we go. Let's head to the lab and get started.